This video is for lesson 18-3, the triangle proportionality theorem. Learning goals are to prove this theorem and its converse, and to apply the triangle proportionality theorem and its converse. Remember that in the last lesson we were discussing indirect measurement by using properties of similar triangles to figure out unknown lengths. Clarissa was a surveyor, and we were investigating different scenarios that a surveyor might measure. Let's say that a surveyor needs to measure across a lake. Well, it'd be very hard to measure directly across the lake, but with use of surveying equipment, if we could find some locations on the land outside of the lake and then use geometry, we could figure out the distance across the lake. Take a look at this drawing right here. Do you see the two triangles? We have the small triangle here, and it's within the corner of this larger triangle that is similar to it. If we have some known distances on the small triangle and then a known distance on the large triangle, we could figure out how far it is across the lake, this distance here, by creating a proportion. We just need to make sure we match up corresponding parts. Let's take a look at a similar question, not about a lake, but just a picture of a triangle. So here we have triangle AST, and let's say that there's a line crossing through the triangle that is parallel to the bottom of that triangle. That means that there are similar triangles. The top smaller triangle is similar to the large triangle. Then, if we made this into a math problem, we could find the length of an unknown side. Let's work on question 3. AM is 12. That's 12. MS is 9. So this much is 9. AR is 15. Determine RT. We don't know how long RT is. We could choose a variable on there, such as a lowercase x. Now we can create proportions by matching up corresponding parts. It could look like this. The 12 is to the 9 as the 15 is to the x. Use cross multiplication, and that would find us the length for x. That problem that we just worked with has to do with the triangle proportionality theorem. When you have a situation like this, where this is parallel to this, then there are similar triangles, and we can make a proportion. The B is to the A as the C is to the D. We're saying that the top section is to the bottom section as the top section over on the right is to the bottom section over on the right. So let's go back to that problem about measuring across a lake. Do you recognize this is that same situation? The triangle has been rotated a little bit, but it still has those parallel sides. So we can use the triangle proportionality theorem. The 27.5 is to the 54 as the 29 is to that distance across the lake. Maybe we call that x. Here's our proportion. We could solve that with cross multiply, and we find the distance across the lake using indirect measurement. We solved that problem about the lake using the triangle proportionality theorem, which is shown here on the left side of the screen. If a line parallel to a side of a triangle intersects the other two sides, then it divides them proportionally. That's what it meant when we were able to make a proportion with corresponding parts. Now on the next page on problem 7, it says state the converse of the triangle proportionality theorem. A converse is when you take a sentence in if-then form and you reverse the order of the sentence. It might look something like this. If a line divides a triangle proportionally, then the line is parallel to the third side of the triangle. What I'm talking about is, let's say there is a triangle, for instance this one, and some line crosses through two sides of the triangle. If we know that this piece is in proportion to this piece, as this piece is in proportion to this piece, then we would know that that line is parallel to that third side of the triangle. Of course, these are going to be actual numbers on here. And so you would take whatever the numbers are, maybe this one is 5, and let's say this one is 4, and let's say this one is 10, while this one is 8. We would be checking to see if things are in proportion. Is 5 to 4 the same ratio as 10 to 8. And if it is, then that line is parallel to that third side. Let's work on a sample problem together. Given that segment RE is parallel to AT, which is parallel to IO, which is parallel to NS, determine each length, show your work. So here we have this large triangle called triangle CNS, and then these extra lines running in the triangle that we're told are parallel to that third side of the triangle over here. That means that all of these side lengths are in proportion. So if we can match up the corresponding pieces correctly, we can find unknown lengths. For example, question A, let's find length ET. So the distance from E to T, right in here, we could call that X for now. We could say that the 48 is to the X as the 36 is to the 24. Now look where I'm getting these pieces. Here's the 48. Here's the X. Then here's the 36, and here's the 24. Use cross multiplication to solve for X, and you'll have an answer for ET. Now I'm going to pause the video for you to try question B. Here's the solution. I chose to call length AI a lowercase y, just to use a single letter instead of using AI. Then I said y is to 24, so I'm taking this piece and matching it to this piece as the 40 is to this length here, which we had figured out was 32. Use cross multiply and I get y equals 30, or AI equals 30. That's not the only proportion that could have worked. For example, we could have taken this piece and matched it to the 36. If we had taken that one and matched it to the 48, you'd get the same final answer, 30. Let's try just one more of these. Work on question C. I'll pause the video for you. Here's a solution. I wrote it up here on the top right of the screen. We were looking for length AT, and I chose to put a variable on there, Z. You could have put a different letter there or even left it as AT. I matched up length AT with that side there, the 27. So I have Z over the 27. And then I compared that to the entire length of this side, which is 60, over this piece here, 36. What I was looking at was a large triangle where AT was the right side of that triangle, and comparing it to this smaller triangle where RE was the right side of that triangle. Well, that problem had no real-world context to it. Let's work on one that has more to do with the surveying scenario we've been using. A land developer is using a surveyor to measure distances to ensure that streets are parallel. If Grant Street and Newton Street are parallel, then what must be the value of X? So here we have Grant Street and Newton Street. We know that they're parallel. That means we can create proportions, but we have to match up the correct parts. One thing I want you to notice is it doesn't tell us anything about this street here, Smith Street. We don't know anything about that. So we can't assume that it's also parallel to Grant and Newton. So when we make our proportions, it will need to look like this. X is to the 320 plus the 450, which is 770. As the 520 is to the 350 plus the 480. Now use cross multiplication and you'll have an answer for X. Here's a check your understanding question. Given the diagram with some lengths parallel, determine the following measures, show your work. Let's work question A together, and then I'll pause the video for you to try the others. Say we want to find length SL, which is this side right here. This time I'm just going to call it SL instead of putting a single letter variable on it. We could make a proportion like this. SL is to the 8 as 48 is to length DE. Length DE is 12. Now in doing this, please notice that I had to figure out how long that was. I have up here some information. All the way across here is 60, and then from here to here was 48. That's how I knew that that bit was 12. Then with cross multiplication, we could find this answer. 12 times SL equals 8 times 48. Divide both sides by 12. 48 divided by 12 is 4, and 8 times 4 is 32. So SL is 32. I'll pause the video. Please figure out B, C, and D. The answers are 36, 24, and 63. In this lesson, we worked with triangles that had additional lines drawn in them that were parallel to one of the sides of the triangle. The theorem that applies is the triangle proportionality theorem, which allows us to build proportions by matching up corresponding pieces. We solved all kinds of problems using this idea.